Thank you. Uh, Hi, everybody. If anybody lives in disgust or boredom, I'll say it's San Francisco traffic, Friday afternoon, so I have the perfect excuse here. I feel very intimidated, like I'm talking into a room containing quite a few people more able than I am. So it's a bit of an oddity here of history, I guess. I was working on my slides, and so I wrote the slides first, and then I titled them, Eric is leaving, San Francisco traffic. I titled the slides at the very end, and the only word, the best word that came to my mind was leverage. I'll explain what I mean by that. Last night, over beers, I got a few questions. I was like, I have no slides, and what do you guys want to hear about? And Gilad said, well, why D? What's the deal with, And, there's two things. There's the party line, and there's also what people told me. The party line is that D offers at the same time convenience, modeling power, and efficiency of generated code. Notice that this troika is hardly offered by other languages. Most languages can offer two of them. The classic PIC2, etc. Some languages go with a lot of convenience and power, but they lack in efficiency. Some languages are efficient but are not that convenient to use, etc. So the party line, this is the party line. Essentially, you're going to find it on the site and everything. I believe it's closely close to truth. Then I talked to people using D, and they gave me quite different reasons. They said, for us it produces fast binaries, fast. Pound for pound, D is the fastest compiler that produces the fastest code in the world. Better than everything that you've been told about until now. It's best to have the last talk of the conference, isn't it? Gotta love it. So it compiles really fast, surprisingly fast. And the code produced is super fast. And there are languages that are faster to build because they don't, for example, don't link interpreters. They're going to be 100 times slower when they execute. There's going to be programs that, that's pretty much it because it can't be much faster than C, right? Other people said it's easier to get into than the alternatives. So they're like, I'm coming from a Python background. And I need an efficient language, and this was quite easy to get into starting from Python. And last but not least, which is kind of an important subjective element, people tell me D is fun to mess with. And that does matter, because a lot of unpaid volunteers have put a lot of hours into it. And if the code doesn't look nice on the page, it's not fun to mess with, then you've got a problem. They're going to start asking for money, for example. Right? So, of course, every language is fun to someone, like every language, at least to their creator, I guess, because otherwise it can't get there, right? Except Objective-C. No comment. All right, so then I got asked, a couple of years later, Charles' story was like, why not D? Why would you not use D? And actually, there's no party line for it. Zero. There's no reason not to use D, of course. But there's people who don't want to use D and don't care for it, and that's totally acceptable. And some of the reasons I heard are things like D is poor on formal specification. It just doesn't have a formalism behind it, and I wish it will have one day. I want to impart a better formal specification on D. That would make it a lot more attractive to people like you guys who research programming languages and do work with languages as opposed to within the languages. It has a few corner cases that are poorly specified. It makes a few promises it doesn't entirely fulfill, things like that. It has little corporate pickup and support. This has been historically a kind of a running joke. Like it's like the penguins on the proverbial penguins on the equally proverbial iceberg. And if one falls into the water, everybody's going to go, but nobody has fallen yet. So they're like, well, is D kind of used? And everybody's, no, we're not using it. And then I'm not going to continue to not use it and that kind of stuff. I have like triple negation there. Anyhow, so it has historically had little corporate support. And fortunately, now I proudly feature, there's a list on wiki.dlang.org, organizations using D, and it's a list of 9 glorious companies, including notably Facebook, which I'm very happy about. So, there's quite a few success stories that are picking up now, including Sociomantic, a German company that's been acquired for $200 million, and it uses 100% D. So, if I were to put a number on it, 200 million is a good start. Doesn't have as many libraries as the more established languages for obvious reasons, and it's a large language. I mean, consider this. Convenience, modeling, power, efficiency. So if you want to cover all 3 legs of the stool, you're going to have a large language. And this is a fact of life. It's a large language. It is not a difficult language to learn, and it doesn't have much accidental complexity because it benefits from the lessons of previous languages and the research that's been going on. But nevertheless, it is a large language. Last but not least, just as when I was about to leave, Mads said, gently provoke in his nice manner. And I said, no problem with that except the word gently. So let's see how this is going to go. So first I'm going to start with a conjecture here. This is going to be a sort of a running thing through my talk. Many language decisions look downright goofy if efficiency is not a concern. So look at a language design that has some efficiency-driven decisions. Like, what the hell were they thinking when they did this? And there's any number of sins committed in the name of efficiency, sometimes for a good, to good effect, sometimes not to so good effect. And the advantage of making slides in the last minute is that we spoke of duality this morning. So I have a duo of my conjecture, which is a lot of language design decisions are great if you don't care about efficiency. So there's a lot of stuff that's, there's nice abstractions that are really easy because efficiency is not a concern. And then there's a great, it's interesting to pursue making them also fast. One thing I like about D is that it turtles all the way down. You know the anecdote, right? Who doesn't know the anecdote? Who does know the anecdote? Who didn't raise their hand? It's the classic joke with infinite regression, like the old lady says, the universe is on top of a turtle, and where the hell is the turtle sitting? Oh, it's on top of another turtle, and where's the hell is the other turtle? And, and so on and so forth, all the way down, right? Infinite regression. So D has turtles all the way down in the following sense. I have the opportunity to also introduce you to Hello World. As Gilad and I were joking last night, people put a lot of emphasis on analyzing Hello World in different languages. Oh, this has 3 lines, this has 2 lines. Better. But, languages are not designed for writing Hello World in them, right? That said, there is something interesting that I want to convey. First of all, this guy kind of looks like a lot like the C Hello World, right? Replace a couple of symbols, etc. It's scriptable, which is nice. The top line is a shebang. It's kind of, you just run it, make it executable, just run it. It's a script. It's not interesting. But it's a simple, correct, scriptable program that features turtles. Let's see. Well, where's the turtle? Here's what I'm going to do. I'm going to put the import inside, right? So the whole import, I'm going to import some standard I/O kind of thing. I'm going to put it inside main, right? If you do the same for a C program, that's a sort of a career limiting move, right? Like you put a pound include inside a main, includes stdio.h inside main. That would be completely weird. And the funniest thing of all is it might actually compile. Do you know why? So there's a thing in C. You can declare a function inside the function, but just declare, and it counts as global. But if you have a struct, it's not going to work. And depending on whether stdio.h declares a struct or not, it may or may not compile. Probably it won't compile. But the funny thing is going to work and kind of in a weird way. Indeed, it works. And it actually works in an interesting way. So you get, I'm saying it's, it's thorough because most everything can be scoped everywhere. So it composes nicely. So, if you can put the import outside a function, why can't you just put it inside and call it a day? And actually, that's an interesting thing. And here's why I think it's interesting. First of all, you have better scoping, reasoning, and dependency management. If I only use write line in one place, in a large module, maybe I want to scope the import inside of it so it doesn't pollute anybody else, right? It's better reasoning because whenever I need, the classic thing, symbols should be as local as possible and all that philosophy, right? So I probably don't need to argue about this at all. Nicer dependency management. What do I mean by that? If I don't use that function, maybe the compiler may take the option to not even open that file. And this is where it gets really interesting because it segues into generics. And here's where all the hell breaks loose, or probably all the hell kind of comes together or whatever. Log. So let's define a simple logging function, and it's a generic function that takes a type parameter t, and it takes some stuff that's of type t. And it needs to print like the current time and the stuff, right? So it needs both datetime and stdio. So it has two dependencies. And now inside main, I'm going to say log hello and whatever, and etc. So it's kind of a simple abstraction here. But the nice thing is, like, if I comment this out and never use the log, it's going to be a template that's never instantiated. It's going to be a generic function that's never instantiated, which means those imports are never going to be needed. So essentially, it's a pay-as-you-go dependency because if I'm not using it, there's going to be no opening the imports, no scanning dependencies, no nothing. And this is where things got interesting. We started rewriting the whole standard library to use the CDM because it's so damn useful, as opposed to eager imports. Now, the funny thing is, true story. One day I was like, let me put this import inside, see what the hell happens. It didn't compile. It was like, oh, semantic error. You can't import there. And I called Walter. I said, can you enable that? Because that sounds like an interesting thing to do. And he was like, well, it's disabled because there's a check against it. And I said, remove the check. Quite literally. And he said, okay, commented out the check and try it. And I was like, it works. It's like, whoa, okay. So it was an artificial limitation. It was a limitation just because our minds were limited. We were thinking in the C thing, in which it's a goofy move to include a file into a function. It's crazy. But indeed, actually, it led to a very nice idiom. And there's some nice kind of implementation details about this, like you don't import the same, you don't actually open the whole file twice, etc., right? There's one interesting effect here, which is the last line here, less pressure on the linker. So if I have generics and things, there's going to be a lot of symbol resolution during compilation in the object file. The way the linker works, it's going to open the object files that you have, and it's going to resolve symbols, kind of look around for symbols and stuff. And then whatever is not solved is going to start looking in the libraries. And that's where like a long kind of time-consuming linear scan is going to happen, right? Which is also system-dependent. It's not under our control, etc. So the more generic stuff you have, the more symbols you're going to solve during compilation. And therefore, there's going to be less pressure on linking, which is like this huge bloated serial step at the end of any build. And the compiler being under control, you can accelerate it, make it better. And the linker is sort of a system thing. And it, even with Gold, it's kind of a lengthy process. So all of this kind of is interesting. And this is chock full of this kind of stuff. Remove artificial limitations. And I'm going to talk about a couple more. But before that, so you can actually define a function inside a function. And even more so, you can define a generic function inside the function, be it generic or not. So you essentially can define a function anywhere. you can define a type inside the function, which is an interesting effect. You define a class inside a function and you return a value of it. And what's the type of the result? Well, it's a type that you get access to because you get the value, but you can't name. Voldemort, right? You can't actually spell the name. Right? The name is inaccessible. And that led to some interesting idioms there because, sometimes these are very much akin to existential types. So this kind of removing unnecessary and artificial limitations has been a running theme in D. One very simple thing, essentially it's next to trivial, but it's been very successful in practice, is a universal function called syntax. So if you have expression 1.fun, expression 2, expression 3, which is a standard member call, right, in C++, Java, etc., right? If the symbol fun is found within the namespace of expr1, then the classic resolution proceeds and everything goes as expected. From here on, this is where the interesting part starts. Otherwise, rewrite as fun and put the expression 1 at the front of the argument list. Right? There's a language that did that way back, and it was called CSOL. I worked on it a bit, and I thought it was a great idea. I thought, oh, how convenient. So I can actually extend types outside their definition, and I don't need to do surgery on classes and stuff like that. And C++ has this unpleasant thing that if you want to add methods to a class, you either kind of do surgery on the class or kind of use a different syntax for them, right? And same about Java. And then C# came with extension methods, right? Do I call them right? Yeah. Extension methods, which are yet another mechanism that achieves the same goal. We wanted something cheap because we couldn't afford the awesome engineer that C# has, so we opted for a rewrite. So it's a term rewrite at the compiler level. It's very simple. And this was like a huge success. Like for these, it was like, oh my God, how much I can do with this. And it sounds crazy, but let me show you. But before I show you an example, let me see where the example is. No. Yeah, okay. You didn't say anything. Okay. So, so the benefit is you can, without invading a type, you can extend its functionality. And all the protection things are respected because we're looking at similar rewrite. So it's not increasing the language size by much. And you can actually extend built-in types. You can add new methods to int and arrays and whatnot, right? And actually, that's how the entire UTF support for D is implemented. And D is great at UTF. It's great for pipes and filters program. I'm going to show this. You're going to love this. And it quickly won the minds and hearts of users. Everybody loves it. So also, it's kind of interesting because there's a default for a method. If you write a method, if you implement it, it's going to take the method. But if you don't define it by that name, you could have a default that takes its place. It's great for generic code. It does have drawbacks. So there's some functions that in which the first parameter does not have a particular meaning, such as like printf, like writef ln, right? So this, I don't know. I guess I could get used to it if I saw it in a code review, but I probably would prefer to write it the format, the first argument explicitly. It doesn't make much sense to put a % at the beginning, right? And this is kind of the most annoying thing. And it was kind of one of those features that interact, but just in a bad way this time. So you have iota of 10 gives you the numbers from 0 to 9. It's a range. It's like whenever you iterate, boom, 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 4, 4, 4, 4, 4, you're going to get 0 through 9. Then you can write 10.iota because of the rewrite noise. Now, well, how about I get the iota of like 10 real floating point numbers, and I get 10 point. And now I write 10 dot iota. And dot is a different token. What? Right? So this kind of sucks. So you got to insert a space here, which is goofy, right? Yes?
It's your language. Take out 10 dot and make it so that you have to have either a suffix f or have a .0. Why do you allow constant numerals be able to be 10 dot? I know the C and C++ did.
Fantastic. Thanks for asking.
Where are the ambiguity?
Yes, so the question was, well, why do you allow dot, numerals like that? Because they are kind of goofy, right? Or dot zero, right? Right? Who the hell, which scientist writes 10 dot or dot zero? Nobody, right? They're going to write either no dot or dot something. For historical reasons. So actually, so you have just echoed a debate spanning millennia about D, right? Did I say millennia? Many hours, I don't know, many days. So actually, this is being discussed. I mean, we should remove that, deprecate, etc. So it's sort of a discussion in progress. Yes.
Isn't another potential risk here that you can have code that breaks with a simple change? Like before, there's no method called iota on your type, and you have you have your extension method or whatever he calls them, and then all of a sudden you go and introduce it, and now what used to bind to that binds to your new method.
So the question was, could you have code breakage that's unintentional? And sort of the example would be maybe you have a typo in the method, and it catches a different function, right? I think that's a risk that's in many cases, right? Even in with base classes and stuff. It hasn't come up as a large drawback. Yeah, I can't recall anything. Yes?
So what happens if you do 10.0.iota?
10.0, that's going to work. Because 10.0 is recognized as a token, and then dot iota is going to be, Yes?
Can you use ambiguity using parentheses instead of space?
You can, yeah, you can. But what all I'm saying is that in...
This is really weird with the space. I'm sorry.
Yeah, it is. I agree. I should have said the parens that could, right? So you could insert a parenthesis or space. To my relief, there's no particular meaning to that 10.iota because that would be killer because you introduce a space or you remove it and it changes the semantics of your program. Fortunately, one of them is an error. So these are the drawbacks. Here's the thing. There is one guy who gives you a language with only advantages. That's a liar, okay? I'm honest until it hurts. Okay? And everything I'm going to tell you about is going to have drawbacks, and I'm going to tell you what they are. Okay? Another one, optional trailing parens. Advantages of building slides in the last minute. Well, if fun is a function, just writing fun evaluates fun. In C, just typing fun did the craziest thing there is. We took its address. And if you put an ampersand in front of it, it does the exact same thing. And that kind of got propagated and kind of remained in the annals of C and C++, and it kind of became a thing. Indeed, we're you have ampersand, so if you want to take the address, you put ampersand there. If not, it's going to be evaluated because that's the useful thing to do. So if fun is a function, you write fun, you get fun, parens. You have object.fun, you're going to evaluate object.fun, parens. And that was very useful. To get the address of the thing, just don't put the parentheses, but just put the ampersand before, and that's essentially that's a grammatical element. Advantages: prints money. As you saw in the quick talk, in the the lightning talk before, essentially this makes money to everybody involved. Less parentheses, like less, like faster development, faster reading, faster writing, less global warming, all that shift presses, that produces heat, right? All that stuff, right? Essentially, it's like free money. It works awesomely with pipes and filters. I'll show you an example in a minute. Disadvantages. Pascal haters gonna hate. It looks like Pascal. You write things like write line, semicolon, and it writes an empty line. And it's like, people are like, I hate that. No reason. I just hate it. And then, that it's a thing, right? Haters gonna hate. There is something more bothersome about that. Ambiguity. What if a function or method returns itself a function? If you put a parenthesis, does it evaluate the original function or the returned function? And the decision is if you add nothing, evaluates only the function. You add one, just the function. You add two, evaluates the other guy. All right. Yes. I'll show you an example. Shazam. All right. So we have a simple program here that takes stdin. It iterates every line of stdin. It filters it such that empty lines and lines starting with a hash are ignored, comments and empty lines. It's going to convert every string to a double, every line to a double. It's going to accumulate everything in an array, because I know how to sort array, I don't know how to sort streams. It's going to sort that stuff. It's going to take the top 10 and it's going to write them. This program is every bit as efficient as one that does everything I just said, very carefully optimized in C loops. Now, all right, careful. Look at the slides. Nothing up my sleeves, OK? This is the program with the parentheses and everything. Look at this. All that noise is gone, right? Including here. Like here, I take the string, I make it into a double. Instead of 2 double of s, I say s dot to double, as if the string had the to method that takes a type parameter double, and it gives you a double. Oh, sorry, the bang. Yeah, so essentially, my plan was to not teach syntax, but just introduce syntax as needed. Bang is template instantiation. Is what angle brackets do in C#, C++, and Java. We found that bang parens are better, because they nest better, right? So you have a lot of nesting going on. So this instantiates the generic function sort with a lambda. This instantiates a generic function too with a single argument. You don't need a parens if there's only one argument. Just you pass double, and that's an instantiation. Of course.
Go back to the previous line.
Yes. The one with the ugly one? All right. Ooh. I hope I didn't have a typo there.
I think this is not, to look at that map double, where the parens seem to kind of
Uh-huh.
appear in their strange place.
I'm glad you asked. So the parentheses are, normally you'd take the stuff here before map, you'd put it in a variable, and you'd pass that variable to map here. But because of the universal function call syntax, you just can put it before. And no function here is a member of anything, although they all use the dot syntax. Nobody's a member of anything. Okay? There are free functions. But if I didn't have the universal function call syntax, what would I do? Well, I would start with write line like an idiot. Right? What do I want to do? Well, I want to write, because that's how I do it. What do I write? Well, the first 10. Well, the first 10 of what? Well, of some sorting. What the hell are you sorting? Well, an array. Where the hell is the array coming from, etc., right? So it would be like a mess of parentheses, and at the end I would have to close like 9 parentheses here. Yes?
I think he was just pointing out the fact that in addition to removing all the empty parens, you moved S to use the universal call syntax.
Yes. So there's 2 working together.
Okay.
So I remove the trailing parentheses, and I use the UFCS.
Could you move it here without and do S.2 bang double empty parens?
Yeah, that's what I did. Look.
Yeah, no, I'm just saying
Ah.
the previous side could have been expressed that way. And
Yeah, so I could have said S.2 double and parens and stuff. Yeah, I just wanted for more dramatic effect here, like Michael Bay.
Why do you have to call filter again? Because isn't filter something that takes a function? Why do you have to kind of put the second parens there?
A generic function has 2 sets of parameters. The bang parens, which are the sort of the generic parameters. In this case, it's just 1 lambda. And the arguments, the runtime arguments, in this case, is the stream you want to filter. So the lambda goes in the types, and the stream you want to filter goes in the arguments, right? So normally it's say filter bang lambda, and then you'd pass the range, right? The std in by line, right? So that's why you need these 2 sets of parens.
It's like of T and BB.
Thanks.
That, I didn't hear that. That was not appropriate. All right. And by the way, the coffee you guys have is terrible. All right, just payback time. Okay. Static introspection is the second thing I wanted to, or the third thing I wanted to talk about. And by the way, what's the time situation?
You can easily take another 15.
Okay.
Yeah, 15.
Right. So static introspection is interesting because it opens kind of a whole new universe that, to like with almost regular code, you write some pretty interesting artifacts. Jon here kind of mentioned, well, it looks like it's unique to D. I thought some languages have it, and if they do, please let me know. But we insisted with static introspection, meaning you statically can inspect types values, entire modules. You can do things like, well, given this module, list me all the elements, everything is in that module. Functions, classes, structs, whatever the hell there is, right? Whatever is in that module, give it to me. For each module member, you can say, well, is it a struct, is it a class, what is it? What's going on? Tell me. For each member of the class, you can say, is it a constant or function, member, method? Is it constant? Is it invariant, immutable? Is it what's going on? Etc., etc., etc. So this is very interesting. It was our bet with D that, because it was when we started with D, it was quite clear we needed some sort of introspection, dynamic, for the sake of a lot of useful things that you can do with dynamic introspection. And essentially I insisted, I said, let's do static introspection, and then dynamic introspection can be easily built on top of it with user code as a library. It doesn't have to be built into the language because you have the static introspection taken care of. And then you come with some serialization protocol and you're done. And indeed, that's what happened. So this led to third simple and systematic genericity. It's absolutely fantastic. Astonishing code leverage. I'm telling you, when I started using this, I would write like 10 lines of code, and that would be complete like bouche bée, pardon my French, like mouth agape, right? Agape, right? Mouth agape. This can't work the way I think it does, and actually it does, right? When it didn't, it was a bug in the compiler. But it's amazing code leverage. It's just you write something and it just does so many things with so little code. Of course, I told you there are disadvantages. There's cognitive load. Thinking what happens during compilation, how to manipulate things during compilation with code during compilation can easily kind of get your mind to explode. But in my opinion, it's worth it. It's a nice challenge to have. And it did delay, and it made non-standard dynamic introspection. Right now, there's like 2 proposals I know of for things like dynamic introspection, and they neither took hold. And it's kind of, they're proposed, people use them, but they're not really standard yet. So let me give you an example. Who knows about things like garbage collection? Who implemented a garbage collector? Oh my God, perfect. Okay, so who has an idea of what the garbage collection does, right? Okay. Eric, what's?
I don't know. I have never heard of garbage collection.
Okay, no problem. It's the dual of garbage creation. All right, comic relief, I can drink some water here. All right, so let me show you an example from a garbage collector, production, a real one. It actually does stuff. So here I'm going to scan something, a pointer to an object. I'm going to scan this guy. And this scan function only applies, it's statically constrained to types that are structs. Okay? So I say, then I'm going to have another scan that's going to apply to arrays, because it's going to be a different function, a different shape. It's going to be another scan for classes. It's going to be another scan for unions, for example, and stuff like that. Very interesting. But this is scan for structures. And structures have fields, right? And fields may have pointers and in directions themselves. And therefore, for each field, I need to kind of continue scanning. But if the field is an int, I don't need to kind of stop there, right? Very interesting. Let's see. Well, if the object happens to be null, nothing to do, return. Here, this whole thing is like, I'm not sure if you remember, but in a mark sweep collector, you kind of mark objects. For each object, there's a bit somewhere in the memory allocator. So you kind of mark a bit, and if you marked it once, you don't need to revisit it again because it recurs forever, right? So you mark it once, and then if you marked it already, you're done. So that's what this guy does. So if it's already marked, then return. Otherwise, it's going to mark the bit, but continue, right? And here I'm going to iterate the tuple of the object, which is essentially enumerates all fields in the object. And my the type of the field is going to be alias to this name for simplicity. And I'm going to introspect this particular type. Does it have indirections? This is a standard library routine, nothing magic. It's really just a library thing. So does this type have indirection? If it does, I'm going to scan this field as well. I'm going to sort of continue scanning. I'm going to recurse. Question, is scan recursive? Yes. At compile time runtime, yes. Is scan recursive? It calls itself, right? So is it recursive? This is a subtle question because it isn't. It is and it isn't. It is. Go ahead.
Tail end recursive.
Huh?
Tail end recursive.
Tail end recursive. It looks like it definitely, but if I have a type of structure with only types of different kinds, it's not going to be recursive. Each instantiation is going to be different. So each scan is going to call a completely different scan. But if this struct happens to have a pointer to another struct of the same type, like in lists, next, previous, whatever, then it is going to be recursive. So with this little code, I cover all structs of containing pointers to themselves on other structs, containing pretty much anything there is to contain. And this is the way you mark things in a garbage collector.
So where do you mark the thing?
It's the second line of the function. So that function mark as used, that's actually either stamping the bit, or if it's already true, it returns false. It does have side effects. It's a garbage collector. I'm allowed. Master, I'm allowed with your permission. You can cut my head if not. All right. So yeah, this is a mutator. So, well, this is kind of an odd thing to write because at the same time, it's not recursive, it's recursive. It's very small. It does a lot. So it has a lot of things going for it. What's the disadvantage? Because there's always one, at least. What's bad about scan?
Is it stamping out specializations for each piece of that structure?
Yes, it's creating one specialization for each instance that's used with the garbage collector. So every type you dynamically allocate is going to generate a separate function for scanning. Okay? The way people traditionally do that in classical garbage collectors, which I saw like a bunch of you have written, is they kind of they use some metadata associated with the object. With like I have pointers are offset at offsets like 8, 16, and 48, and these are my pointers. I'm going to go there and kind of mess with them, right? But in this case, it's all kind of static. So you plant a pointer to this function whenever you allocate an object, and then one indirect call, everything else is going to be direct call. Now that's going to generate. It's going to be a pay-as-you-go. It's going to generate more functions specialized for each type you allocate dynamically. If you allocate few, you're going to have few. If you allocate many, you're going to have many. And that's the trade-off. You got to measure and see how it works. The sheer fact you have the option is pretty amazing. Yes?
I'm curious. So that has indirections, bang F, what is that doing? Like, is that a meta-programming thing where it's looking at
Has interactions bang. So as I said, bang is just instantiate, right? So this is a sort of parameterized Boolean, right? So has indirections actually looks at the fields and sees if any of them is an array, a pointer, or a class. And that's it, right? And the only reason I wanted to plan that guy was to not generate a scan function for everything, right? I don't want to generate scan of int that's just not doing anything, right?
Directions is like a static function or something?
Yeah, so it's you can think of it as a static function. And I'm going to talk about a bit more about that kind of stuff. All right. There we go. Yes, Mads.
5 minutes.
Oh, thank you. All right, compile time evaluation. So this comes, exactly kind of segues with your question. Indeed, you can evaluate entire program fragments during compilation. I know it's laughable, but in a good way. So you can actually create new object during compilation. And you mess with it during compilation, then you're done with compilation, it kind of freezes in suspended animation, and you continue during runtime kind of messing with it. You can math, no problem. You do strings, no problem. And even if you kind of mess with strings enough, you can create a program that you're going to evaluate during compilation. Actually, this is a thing. You can create a string that's a program during compilation, and then you can evaluate it during compilation or at runtime, either way you want. Pretty amazing things have come out of this, including like grammar specifications that are embedded DSLs, regex that's faster than the best in the world, stuff like that. All right. However, there's always a rub, right? Compilation may never finish. You have an infinite loop somewhere, right? That's why I'm saying less than or equal to infinity, right? It may take very long, or may never finish. What?
Can the compiler kind of delete all your files?
It can't. So it can't make system calls. I should say, what's missing is also as important as what's there. You can't evaluate system of rm-rf/, right? You can't do system functions and stuff like that. You can, however, evaluate everything that's sort of in the language. David?
Do you want to take a wisecrack?
Wisecrack, destroy.
So, no, this isn't a critic. This is like, so if when it evaluates my program fragment during compilation, it gets an error, does it wait to tell me till I actually run the program?
Uh-huh. Good one. Well, you kind of touch on a nerve there because errors with, like, you generate programs, we evaluate them, and you kind of generate other programs and evaluate them, and it gets bananas real quick. And we have an error in the midst of all that. It's very difficult to figure out the origin of the error. So there is a problem with attribution and stuff like that. Blame, right? So, all right. Static if is a very simple construct, which I actually featured already here. You see there's a static if has indirections. It's very simple. It statically include or exclude code depending on Boolean expressions. But the interesting thing is static if works with everything else. So it compounds with everything else because you have Boolean expressions, but there can be arbitrary Boolean expressions that you get to compile during computation, compute during compilation. I know, 2 minutes. It's crazy. And using introspection and stuff. So you get to like the full gamut of everything. You can use Boolean logic as your ad hoc type system there. And you have much more interesting things than just types to mess with. Which is interesting because I was talking with Martin Odersky, and he came with these complicated types that expressed some realities. And I was like, oh, but the Boolean equivalent of that is much simpler. I was like, oh, that's kind of bizarre. So the comparison, when I got into using static if, I felt as if so far I'd written like programs without if, and now I have if. You could write ordinary code without if. You could use the question mark, colon operator. You could use pattern matching in function languages. You don't need if, right?
Use APL.
You could use APL, which I don't know what the hell is. You could, what does APL do?
Everything.
Everything and anything.
In one line.
Oh, yeah, it's the thing that game of life in one line. OK. So essentially, you could code without if. And people, it just can. It's not a deal breaker. Could do things. But if you have if, it's so much more convenient. And I felt the same with switching from C++'s lack of static if to having static if. It's just amazing. The disadvantage is you can't have race conditions during compilation. Static if expression introduce a variable. Static if that variable introduce another variable. And you have the classic race because compilation is parallel, right? All declarations are entered in parallel. So we haven't really defined that well. So we're counting on users not doing that kind of stuff. The thing is that the key point here is they work together. Either any one of these little things that I told you about would suck if it weren't in conjunction with everything else. Static if is like, pound if on steroids. Who cares? Who gives a damn, right? But no, wait a minute. We have Boolean evaluation, all that good stuff. And it works with static if. And wait a minute. We have this compile time evaluation of stuff, and awesome. And wait, we have these parentheses that you don't need to put, and it works with pipes and filters, and it looks like you write in a 5-line and write a full sorting program. And it's pretty nice. That's the key. It's working together. Let me give you an example. This again from my recent work on an allocator. This is production code. So it has a lot of details I'm going to throw at you, but worry not. There's 2 key points I want to make. That guy and this guy. So what this does is reallocates. Given an allocator, it reallocates a block of memory to a new size. So now here's the thing. First of all, you should know that the moment you have an inefficiency here, you're lost, because this is a razor-thin margin business. Allocation is like you got to be like super fast. Like it's a dark matter of computing and memory allocation. So you got to be like super fast. You can't waste any cycle. So here I'm statically introspecting the allocator. Do you have a method called expand? If it does, then I'm going to say, well, let me kind of try to expand. If I manage to expand, I'm done. In-place expansion of memory. Awesome, fast. And then I'm kind of doing the, I can't expand, or if the allocator doesn't even know how to expand, then I'm going to do things like, well, let me allocate a new block and copy the old block into a new block and all that crap, right? And now maybe I have an allocator that uses tracing. It doesn't know how to deallocate memory. You know, garbage collector. If it doesn't know how to deallocate, I'm going to skip this part. But if it does know how to deallocate, I'm going to deallocate. Now, here's the point. How many lines do I have? Maybe, I don't know, 20? 20 lines. But I wrote 4 functions. There's 4 functions in these 20 lines. For the all binary combinations of has or has not, these 2 methods. There's 4 functions. In C++, I've written 4 functions. In fact, a guy wrote 4 functions because he ported my D stuff to C++. That is the thing. So what I have here, I didn't write 1 function, I wrote 4. For each combination, I tweak the code. It's very plastic, very easy to mess with. And I hope it's very easy to read. Does it make any sense? I see nods. All right, how many minutes? -1?
-2.
All right, here's the slide. Here's the slide. So after I wrote all this crap, right, I was like, what am I thinking of? What's the theme here? I think it's leverage. I hate writing code. I like writing 5 lines, and these are the best 5 lines I've written in my life. I like this stuff. I wrote a system that's like 48,000 lines of code and it does this, right? Perceiving a system that's like 2 million lines of code. I like small examples. I like small code. Leverage. You write a lot less code with a lot more behaviors. And the way I see this kind of static code molding with static if and compile time evaluation, introspection, the way it works is it's really lossless code compression. You compress code. You compress a lot of code into fewer lines. And you can take it and kind of put it in an anvil and just compress the thing. And then you look at the code, and it's like so many behaviors because it has all of these, these decisions and controls and stuff. Feature interoperation is key. Rapai said yesterday, the way features interoperate is as important as the features themselves, and I totally believe that. So the interesting conclusion here would be that if you have genericity and if you have static introspection, you get into generating code. And with this, I'm done. Thank you.